I want us now to look at this one. This is question 8 of the May 2025, the June exam. Okay. Look at this question. We're going to try and answer all the question on this question 8. And they say that the simplified diagram below, it shows that it shows a cell that can be used to measure standard electrode potential. Let me quickly highlight that because it looks like on this lesson we're going to talk much about standard electrode potential. Okay, they say of the halves or of the half reaction represented by the equation below, we can see the equation, we can see the diagram, guys. I don't want to go much into this diagram. I'll definitely explain everything as we are busy answering the questions. Okay, so I'm going to explain each and everything into detail. So this tells you that even if you look at 8.1, 8.2, 8.3, those are 1 mark questions, right? But I'll go into too much details. I'm going to, guys, I'm going to take time to answer this because I need you to understand how this works. Even if the questions, when you get in an exam, you find something like this, you'll be able to master the question. Even if the questions look different, you should be able to master the question the way I'm going to explain this one. Okay, so the first question says for solution D, write down the name or the formula of ions needed. Okay, for the solution D, this is your solution D. This is your solution D, and they want us to write down the name or the formula of the ions needed. So I'm going to give you guys step by step what you need to do. So this is what you are given. So first thing first, we can first start. So the first step to answer your 8.1, I'm going to say for this 8.1, okay, so to answer 8.1, first thing first, let me do this. Okay, so first thing first, I need you to identify the right hand cell. Okay, so that's the first step. You're going to identify the right hand cell. Okay, so I need you to say step 1. Let's identify the right hand cell. Okay, so looking at this, the right hand half cell, the right hand half cell, let's say the right hand half cell. Okay, half cell. So I'm going to look at this. Look at this. The diagram shows they said the question said write down for solution D, write down the name of the formula of the ions. And the solution B, we can see that in that solution, we need to, it's happening where the diagram shows the hydrogen gas. Okay, so it shows the hydrogen gas. That's what we note on that. It shows the hydrogen gas, H2. So since it shows H2, we need to list all the things that we see on the diagram. We see H2. What else do you see on H2? We see a platinum electrode. Okay, so we also see a platinum okay, so that's what we see, a hydrogen gas, platinum electron, and we also see a solution that contain ions. That's what we see. Okay, solution containing ions. Okay, so now what you're going to do, we can see that this setup is the standard hydrogen electron. So therefore, by looking at what we are given here, then we have to conclude that the setup for this is what we call the standard hydrogen electron. Therefore, the setup the reason I want to explain everything is because some of these things we're going to need them as we keep on moving. Okay, so this is the setup is the standard electrode. Standard electrode, the standard hydrogen electrode. Standard hydrogen. And we know that this is what we call the SHE. Okay, so now, what is this? We know that if this is the standard uh, hydrogen electron, the SE, we need to write down the SHE half reaction. We need to write down the SHE half reaction. Okay, I'm just gonna write that down. So what will be the half reaction for that? Because we know that this is the hydrogen gas. So if you go to, let me quickly, just gonna duplicate this question paper here. Then we'll definitely go at the back of the question paper, and then let's go find that for hydrogen. Let me look at where is hydrogen. Okay, let me see. Where is that hydrogen? Okay, so I'm looking for the hydrogen, the H2. I can't see the H2, guys. And I know that you can see it on your side. Oh, there it is. Look at this. So this is the H2. I just want to write this down. So this is the H2. I'm just gonna take this reaction and then let me go and write it that side. So this tells me that the SHE half reaction will be 2 of the H atoms, and then they are in aqueous solution. Then this has 2 of those electrons. Then this forms the hydrogen gas. So that is the half cell reaction. Okay, so from this half cell reaction, I need you to determine the ions that are required. Okay, so the ions that are required, we're going to say that for the equation, we can see that the hydrogen ions are required. Look at the equation. The hydrogen ions are required. So they must be present in the solution. So since they must be present in the solution, what I'm going to tell you guys is that please note that when we talk about the standard hydrogen electron, this guy here, it always has the following. It always has the gas, the hydrogen ions with the concentration of 1 mole per decimeter cube, and also the platinum electrode. Okay, then so the hydrogen ions are the ones that are required. So to answer this this question here, the answer for this is going to be the hydrogen ions. I hope you guys understand how we got that answer. I'm very sorry guys for taking so much time to get to the answer. So the answer for this one is the H plus, right, so that will be the answer. So guys, I don't want us just to refer to the memos. You need to understand the answer from the memo. Where is that answer coming from? 8.2, write down the initial reading on the voltmeter. Even this one, I'm going to take my time to answer that question. So for 8.2, I'm going to definitely take my time to answer that guy. So look at what we have now. on this 8.2. So I'm just going to put my 8.2 down there, and they said that we are looking for what? Write down the initial reading on voltmeter. So look at this diagram. We need the reading on voltmeter. So what will be the reading on voltmeter? So the first step, I need you to understand what the standard electron potential mean. Okay, so you need to understand what the standard electron potential means. So a standard electron potential is measured relative to the standard hydrogen electrode. Okay, so the scientists, they chose the He as what? As the reference of the electrons, and they assigned it the reading of 0. Okay, 0.00 volts. Okay, so even if we can go there on the periodic, you'll see that they chose the SHE and they assigned it the E of 0. Okay, so let me go back and see. Since this is the case, now that you understand what the standard hydrogen electron mean, it means that it's measured relative to the standard hydrogen electron, and then the reference electron that they assign is 0.0. So now what you're going to do, you're going to determine the standard electron potential of the ion half cell. Okay, so let me write this down. So we're going to determine the standard electrode of what? The standard electron of the ion half cell. Okay, so let me quickly work on this one. So if you look at this, we have the given half cell reaction. Look at the half cell reaction that is given there. Let me quickly indicate which one. So look at that half cell reaction. I think you can see the half cell reaction that is given. So let's look at that. I'm just going to take that and rewrite it here. So this is the given half cell reaction. We are given that the ion with the 3 plus charge, it is in aqua solution. Then this guy, it has okay, that's an electron, and then now we have the Fe 2 plus in aqua solution. So looking at this equation from the standard reduction potential table, I'm just gonna go to the standard reduction potential table. I'm gonna look for Fe is the one that is the charge of 3, which is this one. So we can see that look at what we have there, 0.0 or 0.77. So I'm going to rewrite this down and say this guy here, it's equals to positive 0.77 volts. Okay, so now we're going to use this information to calculate the cell potential. Okay, so we need to calculate the cell potential. So you're going to calculate the cell potential. Right. So when you calculate the cell potential, remember the formula. In most cases, you'll definitely be given the formula, right? So the formula for the, let me go back up. The formula should be here on the formula sheet. And this is the formula that we're going to use. Okay. So it depends on what you are given. It depends on what you need to work on. So in this case, the formula that we're going to use, it will be E of the cell, it's equals to, we're gonna take the 1 for the cathode, and then we subtract the 1 for the anode. Okay, so now what's next? we're going to substitute in our values. We're going to substitute in our values. We need to understand which one is the cathode and which one will be the anode. Okay, so looking at this, we know that the one that is given, which is this one here, this guy here is going to be my anode, and this one here is going to be my cathode. This is my cathode. Okay, so when I do the substitution, this will be equals to, I'm going to take the positive 0.77, I'm going to subtract the 0.00, which just gives us 0.77 volts. So the voltmeter is 0.77. That's your final answer. Okay, so now when I look at this, I think we are now ready to work on 8.3. So let me see what we have on 8.3. Which electron, A or B, is the cathode? So between A and B, which one is the cathode? Please don't do guesswork. Make sure that you understand how to answer this question. Which one is the cathode? So now I'm going to say that for us to understand which one is the cathode, this is what I'm going to do. Remember, you need to recall the definition of a cathode and also the definition of an anode. That's what you need to understand in order for you to get this 8.3 correct. So I'm going to say that a cathode, if I say cathode, this guy, this is the electrode where the reduction occurs. Okay, where reduction occurs. Okay, then since this is the cathode where the reduction occurs, I'm going to give you a memory trick. I think they already gave you this at school, where they say the red cat. Think about the red cat. Okay, think about the red cat. Reduction or cathode. So think of the red cat. So reduction occurs at cathode. So the red cat means reduction occurs at cathode. Okay, so now that you understand what is the meaning of the cathode, you have to examine the given half reaction. Okay, so let's examine this given half cell reaction. I'm going to examine it, and then from this, look at this. Tell me what you notice. I'm just going to rewrite the half cell reaction, and then you're going to tell me what do you notice? Okay, so let's rewrite this equation down. What we are given from this is that, I'm just going to rewrite this down here. We are given Fe 3 plus, which is in aqua solution, plus E, and then the Fe 2 plus, and then this is in aqua solution. Okay, so what do you notice from this equation? What do you notice? Can you see that the Fe3, this guy here, it gains an electron. So this guy gains an electron. Right. And then if it gains an electron, what happens when we talk about gaining of electrons? What comes into your mind? The word gain an electron. This tells you that gain of electrons means reduction. Okay, gain of electron means reduction. Therefore, we can conclude and say this reaction is reduction reaction. So the given reaction, so this given reaction, we're going to say is the what? Is the reduction reaction. Is the reduction reaction. So this given reaction, we're going to say is the what? Is the reduction. 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 Is the re reaction. Okay, so since it's the reduction reaction, I need you to locate where the ion half cell is. Okay, so to locate where the ion half cell is, we can see that if we look at this, the Fe3 plus, the Fe3 plus, or the Fe2 plus half cell. Look at where is that half cell. So if we can understand on the given diagram where is that half cell, that's where you can see which one. The question was which electron A or B is the cathode. Okay, so now what I'm going to do, when I look at this, the Fe3, because already we know that this is the hydrogen gas. So the one on the left hand side, which is this one, is going to be what? This one is going to be the Fe3 plus or the Fe2 plus, right? So this is on the left of this diagram. Therefore, the reduction occurs at electrode A, right? So we know that we said that the cathode is where the reduction occurs, and we can see that the given half cell reaction is the reduction reaction. So since it's the reduction reaction, we need to check between electrode A and B which electron is for that reaction, is for that given reaction, which is electrode A. So the electrode A is the one that will be the cathode. I hope you understand that part. So this makes this guy to be the cathode, and electrode B, this will be the anode. Right. Now, let's keep moving to 8.4. Let's see what we have on 8.4. 8.4 says, explain the answer to 8.3. So now this makes sense. You're going to see why I need to give you guys all this information. Why should we go all the trouble to understand this question? Look at this. They say, explain the answer to question 8.3 in terms of relative strength of the reducing agent. Or I'm going to massify you on this one. So now they say that in terms of the relative strength of the reducing agent. So now we need to explain that 8.3. Why is B the cathode? Okay, so we need to identify the reducing agents first. So we need to identify them. Let's quickly work on that. Okay, so the first step to answer 8.4, you need to tell the marker. It's fine because it's fine. I'll definitely go to the next part, because if you can see on the memo, they'll just give you the answer, but you don't understand where is that answer coming from. This is what I'm doing. I'm just explaining how they got the answers, you understand, so that it can be easy for you to study. So now, when I identify the reducing agent, that is step one. Let us start there. You identify the reducing agent. Okay, so when we identify those guys, we know that the reducing agent, so when I say reducing, a reducing agent, this guy, it loses electrons. Okay, right. So when we look at the, I need to write the, maybe let me look at the hydrogen half cell. So if I look at the hydrogen half cell, so the hydrogen half cell is H2, which is in gas state. Then this gives us 2H plus in aqua solution, then plus 2A minus. So now if you go back to this, look at how it is on the table. How is that on the table? Look at this guy. Then now you're going to know, to understand what is going on. Look at how you get it on the table, and look at how I'm going to write it on this part. Can you see the difference? Is that, remember, we said the cathode is electrode A and the anode is electrode B. So this tells you that at the cathode, that's the reaction, and then at electron B with the, which is the anode, this is where we're going to have the oxidation. So the oxidation is the one that loses electrons. So the hydrogen gas is the oxidation. So whenever you lose electrons, just know that the E will be on the reactants. Whenever you gain the electrons, just know that the E will be on the reactants. That's why I have it there on the reactants, because this is gain electrons, it's on the reactants, and then wherever you lose electrons, this guy is on the products. I hope you are happy with that part. Make sure that you don't forget that. Né? If you gain electron, the E will be on the reactants. It's on the reactants. And then if you lose electron, the 2E, it will be on the product. So now, since we said that electrode A, that's the reaction, then for the hydrogen one, we should write it like this, because this is a loose electron. That's how it should look like. Okay, massive. Now, when I do this, I'm going to say that, look at the hydrogen. So the hydrogen gas, we can see that from this information, the hydrogen gas, it lose what? The hydrogen gas lose electrons. Okay, so the hydrogen, this is not going to be there. I'm not sure you guys will be happy if I use that marker. Okay, so we are saying that the hydrogen gas, this guy, it loses electrons. Look at this. Reducing agent loses electron. And now we can see that the hydrogen gas is the one that loses electron. So this H2 is going to be your reducing agent. Okay? Please give me a second. You'll see where I'm going with this. Né? Just give me some time. Everything will make sense now. Then I'm going to look at the other reaction. So the other reaction that I need to look at, remember this is the reaction at electrode B. I'm going to look at the reaction at electrode A. So the other reaction, which is the Fe, I can say this is the Fe2 minus, remember, look at how it is given there. So this is not the actual one, okay? We need to look at how it is given there. We can see how this is given there, but that's not how you should write it. Remember, we should write it as a half cell reaction, okay? So that we can understand, we can see that this one is the reduction, is for the reduction. So this is how I'm going to write that reaction. I'm going to say that 2E plus, then which is in aqueous solution. Look at this. It becomes the Fe3 plus, which is in aqueous solution, and then with E. Right. So when I look at this, look at what is going on at the Fe2. Okay. So the Fe2 is the one that loses an electron. This guy here, it loses an electron. Okay. So since it loses electrons, therefore this Fe2, it's also a reducing agent. Okay. So now we need to compare. We need to compare the H2 with that Fe2 plus. How do we compare these two guys? Easy. When you compare them, you're going to look at the standard reduction potential. This guy here has a standard reduction potential of the 2, let's say the 2H plus or the H2. This guy has the standard potential of 0.00 V, and then this one has the standard potential of what? The standard reduction potential of the Fe 2 plus or the Fe 3 plus. This one will have the standard potential of 0.77 V. Okay, so since this one has, let me write this down. Since this one, it has more positive, let me write this down. It has more positive value. Okay, since it has more positive value, it's going to have, gonna say it has more or has stronger tendency to be reduced. Let's not say more, but let's say stronger tendency to be reduced. Has a stronger tendency to be reduced. Okay, so now therefore this tells you that the one that has a stronger tendency to be reduced is going to be a weaker reducing agent. So this guy is going to be a weaker reducing agent, and this will make the hydrogen gas to have a stronger reducing agent. This will be the stronger reducing agent. So now you know how to identify which one is there, which one is the stronger reducing agent and which one is the weaker reducing agent. Guys, I'm not just answering the question paper, I am teaching you. Just in case they change the question in an exam, you'll be able to answer them. Okay, so now what I need you to do, now that you understand which one is the stronger reducing agent, which one is the weaker reducing agent, let's say in an exam they might also change the question and say identify the stronger reducing agent or the weaker reducing agent. I think you'll be able to find that, right? So next thing, I need you to explain what the stronger reducing agent does. So to answer the question, you're going to explain what the stronger reducing agent does. And so okay, so now we said that the stronger reducing agent, it loses electrons more easily. Okay, so the stronger reducing agent, so this guy here is going to, it loses electrons easily. Okay, so since it loses electrons easily, therefore the H2, this reaction is going to the hydrogen gas lose electrons. So this one, it lose electrons. Okay, so if it loses electrons, and then the electrons move through the wire to electrode A. So if you look at this, the electron will move through the wire to electrode A. So this will be my electron moving. So these are my electrons going in that direction. These are my electrons. There are my electrons leaving from B to A. So now we know what is going on here. This will be that electrons moving. These are the electrons moving. So the electrons move through the wire to electron A, and then at electrode A. So at electrode A, we can conclude and say, therefore at electron A, the Fe 3 plus is the one that will gain that electron, right? It will gain that electron and become Fe 2 plus in aqua solution. Okay, so this Fe is going to gain electrons, and it will be reduced. Right. So I'm just gonna try and conclude this now. I'm just gonna try and conclude this now because I can see that I'm having so much time now. To answer your question on 8.4 regarding the information that we discussed, we're going to say that therefore the answer for 8.4, we're going to say H2 is a stronger reducing agent, right? That's the first thing that you need to tell them. It's a stronger reducing agent than the Fe3 plus, or you can say the Fe2 plus, right? So maybe for sure you see the memo, they say the H2 is a stronger reducing agent, but you don't understand why. But now I think I've explained that now, and therefore we're going to say that it loses electrons. It loses electrons more readily. Okay, so since this is the case, the electrons flows to electrode A. So the electrons where that Fe3 plus will gain them. And when it gains electron, is reduced. Okay, I hope you guys are happy about that answer. Eh? I know that we are taking so much time. It's fine. It's fine. We are learning here. It's reduced to the Fe2 plus. Okay, so since the reduction occurs at electron A is the cathode. Okay, so A is the cathode. So this is your answer for that 8.4. But now you need to understand why we are saying H2 is the stronger reducing agent than F2. The reason, if you understand that, you need to go through all these notes, okay? You need to go through all these notes. Oh, let's see what is the next question. The next question, 8.5, they say write down the name or the formula of the metal used as the electrode A. Wow. Uh, they say, I know that you guys already know the answer for this one, the name of the formula. Let's examine the half cell and then we'll take it from there. They want the name of the formula of the metal used as electrode A. Okay, so when I look at the given diagram, let's examine this. We can see that the half cell reaction, it contains, so to answer 8.5.1, I can see that the half cell reaction contains the Fe 3 plus ions, and then it also have the Fe 2 plus ions, and then both of these substances are in a solution. There is no solid ion metal present. Okay, so then now we're going to determine the type of electron required. So since we say that there's no solid ion metal present, let's determine the type of electron required. Remember, because no metal participate directly in the reaction, an inert conducting electron is required. So for this to do, we require inert conducting electron. Okay, so since this is the case, we're going to say what are the inert conducting. I'm referring to the platinum, PT. I'm referring to graphite. Okay, and the formula for graphite is C. But remember, we said that this is a standard what? We said that this is a standard electron potential measurement. So the platinum is used. The correct answer is platinum. Why? Because this is the standard electron potential. So the platinum is used to answer 8.5.1. The answer for 8.5.1, it will be platinum. Okay, so when you write it, say that, okay, let me just move to the next one. Next question. Half cell reaction that occurs at electrode B. They want us to find the half cell reaction. If you still remember from 8.3, from 8.3, we say A is the cathode, therefore B must be the anode. Okay, so let's quickly write that down. So we said that this is the anode, and then we said A is the cathode. Okay, so now we need to recall what happens at the cathode. At the cathode, oxidation occurs at the anode. So the anode, this will be oxidation. This is where oxidation occurs. And then at the cathode, we're going to have reduction. Okay, right. So now the hydrogen half cell reaction, we know that the hydrogen half cell reaction, oxidation, that's gain of electrons, reduction. What am I saying? We said reduction, gain, oxidation, lose of electrons. Okay, so now we know that the hydrogen half cell reaction, if you still remember, the hydrogen half cell reaction was the H plus in aqua solution, 2H plus in aqua solution plus 2E, it forms hydrogen gas. This is just what we got from the table, as you can see there. This is what we have from the table. Okay, so now because oxidation occurs at B, look at this. The oxidation, it occurs at B, and what is the question saying? The question says the half cell that react occurs at electrode B. So since the oxidation occurs at, this is 8.5.2. 8.5.2. So since the oxidation occurs at electrode B, we know that oxidation is what? Let me go back up. Oxidation will be, where is that thing? Reduction, gain, which makes oxidation to be loss of electrons. Then you need to reverse the reaction. You see this reaction here, you need to reverse it. Okay, so you need to write it in reverse. So when we write it in reverse, so to answer that 8.5.2, the answer will be H2 gas. You reverse that reaction, then the 2H plus comes this other side. Then remember, another thing that you can remember is that we said if this is oxidation, if this is oxidation, we said that the E should be on what? The E should be on the product. Wherever you okay, so oxidation, loss of electrons. Wherever you lose the electron, the E should be on the product. That's why I'm saying reverse the reaction, and that will be definitely, that will be your answer. That will be your answer. Let's look at the next question. The cell notation for this half cell. So I'm going to show you a quick way to understand the cell notation. Okay, so this is how you write the cell notation. Let me make this to be let me make this easy and easy and easy. So this will be 8.5.3, and we are going to work on cell notation. Let me give you, let's say you are watching this today and you are writing tomorrow, then this tells you that tomorrow is today it's your lucky day. I'm going to show you a way to cram this. Okay, so first thing first, I want you to write the anode on the left. That's what you need to understand. You need to write the anode, you write it on the left. Okay, so let's identify the anode reaction. If you still remember the anode reaction. So the anode reaction was a reaction at electrode B. So the anode reaction we said is going to be this one, the one that we said reverse the one that is happening at the anode, which is H2 in gas state, and this forms 2H plus, and then in aqua solution, then plus 2E minus. Okay, so that is the anode reaction, right? So the cell notation for that, for the anode, remember we said we write it on the left. So the cell notation, you start with the, let's go to 8.5.1. 8.5.1, was that 8.5.1? Yes. The metal. We're going to start with the metal. You first write the metal, okay? So we said the metal is platinum and it's in solution state. So it's going to be platinum. The cell notation will be PT. Then you're going to say it is in solution state. Then you're going to put something like this, a vertical line. Then you're going to look at this. You write the way this thing it is on your anode reaction. You write the H2 first, then the 2H plus after. Okay, so let me quickly put that. So you're going to say this will be the H2, which is in gas state. Then you're going to write another arrow, and then you put the H plus. Please, when you put the H plus, don't include the number in front of that H. So this will be AQ. Right. Then, when you are done, you're going to draw a what? You're going to draw a salt bridge. So this is step one. You write the anode on the left. You need to first write the anode reaction. Then, on number 2, you're going to write, you draw the salt bridge. And what is the salt bridge? It is denoted by the symbol like that. And then you're going to write the cathode number 3. You're going to write the cathode. You're going to write this one on the right. Okay, but before you do that, write down the cathode reaction first. Cathode reaction. What is the cathode reaction? We said if you look at this, the cathode reaction is gain of electrons. So the A will be what? The A will be on the reactant. So it's going to be Fe 3 plus. It's in aqua solution. Then this reacts with that A. It's on the reactants to show that we are gaining electron. Fe 2 plus, which is in aqua solution. So when you write your cell notation for this one, you're going to say the cell notation, just write it the way it is. You start with the Fe 3 plus first, you do an arrow like that, but indicate that the Fe3, the Fe3 plus, it's in what state? It's in aqua solution. And then draw that. We're going to have the, what's next? This will be the Fe 2 plus, which is also in aqua solution. Then we draw that. Then you're going to put the platinum at the end. So the trick here is that on the cell notation for the anode, you start with the metal, and then you're going to end with the metal on the cell notation for the cathode. Then you combine these two by first writing, this will be the first one, which is on the left, and this will be the second notation, which is on the right. So let's write this. I'm going to write everything that I have there. So this will be, the platinum is going to be, the final answer will be PT in solid state. Then I have the H2 in gas state. Then I have the H plus, remember, don't include the 2 in front. Then we're going to separate the anode and the cathode by using a salt bridge. So you separate the two by using a salt bridge, then you write that one up. So this will be the okay. See, now I'm putting a plus sign. Then this is Fe2 plus. Then this is in aqua solution. Then this is the PT, which is in solid state. Then you are done. You'll definitely get all the marks. That should be the marks for this one. Okay, so now on 8.6, they say, give a reason why the voltmeter reading drops to 0 after the cell has operated for some time. And they want us to answer that question for 1 mark. Okay, so to answer this question, give a reason why the voltmeter reading drops to 0 after the cell has operated some time. To answer this, ladies and gents, you need to understand, number one, you need to understand what happens while the cell operates, okay? So that's what you need to understand. So ask yourself a question. What happens if a cell, okay, not if, what happens while a cell operates? Okay, so now we're going to look at this. We know that at electrode A, at electrode A, we have the Fe 3 plus in aqua solution and reduction, gain of electrons, Fe2 plus in aqua solution. This is at the electrode, right? So now what's next? We know that at electrode, we can note that this guy here, the Fe3 plus, it decreases. And then the Fe2 plus, it increases. Okay, right. So that is what is going on at electrode A. Now let's examine what is going on at electrode B. So at electrode B, remember the reaction was like this. This is not in aqua solution. Hydrogen, it's a gas, that's a gas. And then this gives us the 2H plus in aqua solution plus the 2E minus. So now what happens is that we can see that the H2 is the one that is decreasing. So guys, the one that is on the reactants, it decreases, and the one that is on the reactants, on the product, is the one that is increasing. Okay, so what can we say? What happens eventually is that as the reactants are used up and the product increase, the reaction slows down. Okay, so eventually the system reaches equilibrium. Okay, so reactants, we are saying that the reactants are used up. Right. So, and the products that are the one that increases, the products increase. So, we can say that the reaction, therefore the reaction, it slow down. So if the reaction slow down, we say that the system reaches equilibrium. Okay, the system reaches equilibrium. Okay, so since the system reaches equilibrium, this tells you that the forward reaction is equals to the reverse reaction. F for forward, R for reaction. So the forward reaction is equal to the reverse reaction. So, okay, If the forward reaction is equal to the reverse reaction, because of this statement, what can we conclude is that there will be no net electron flow that occurs. Okay, so now how will this have an effect on the voltmeter? How will this have an effect on the voltmeter? So this will say that if the electrons stop flowing, if there's no flow of electrons, it tells you that electrons, they stop flowing, right? So if they stop flowing, there will be no potential difference that exists. And then the voltmeter reads 0. So the voltmeter, it will read 0. Right. So the answer that you can give them, the final answer, you can say that the cell eventually reach equilibrium. So I'm just going to try and write this. The system reach equilibrium. I just wanted to first explain how the system reach equilibrium. That's one. And then you say at equilibrium, there's no net electric flow. So therefore, there will be no net. This will be true on your statement. And then through the external current, there will be no net flow, right? Therefore, the potential becomes 0. Then this will be potential reach 0, that's 3. So if you can say system reaches equilibrium, no net electric flow occurs, and the electron stops at the potential, not potential difference that exists. Of course, you'll definitely get all the marks. And this, guys, this question, we did 1 hour on that question. And guys, I'm very happy that we did an hour on that question. So yeah, and that's it for this one. This is how you answer the question. Guys, I just enjoy when teaching chemistry. This is why I uh, wanted to go through all this, so that even if they try to change the question, you will still understand the question.